Hi there. Let us take up another law that is called Henry's law, that is applicable for liquid gas mixture. Solubility of gas in a liquid, like oxygen is soluble to the extent in water, in all the water bodies, that makes the aquatic life possible. So let's see how we can correlate the Henry law applicable for a gas liquid mixture correlated to the Raoult's law, that was for liquid mixture, and also modified for a liquid non-volatile solute mixture. Now the modified Raoult's law will be called Henry's law here for the gas liquid system. This is the 9th lecture in a row for the liquid state solution. Now, the factors which influence the solubilities of gases in liquid, for example, water is a universal solvent. So the factors influencing the solubilities of gases are, number one, nature of gas, whether it is a polar or weakly polar or completely non-polar. If they are completely non-polar, like oxygen, nitrogen, hydrogen, helium, argon, carbon dioxide, which is a linear molecule, so there is no net dipole moment, methane and other hydrocarbons are completely non-polar and they are sparingly soluble in strongly polar solvent like water, because you know the principle, like dissolves like. Birds of same feather flock together. So the solubilities of all these non-polar gases is very, very small, but we have to study. However small the solubility may be, we must study about it and have a law to quantitatively determine the solubility with the pressure, that is external pressure in equilibrium with the liquid gas mixture. There are some polar gases like ammonia, sulfur dioxide. They are soluble and a large part of it remain undissociated, hydrated but not dissociated into ions. But highly polar gases like hydrogen chloride, hydrogen bromide, hydrogen iodide, they undergo complete ionization, are highly soluble. These polar gases, ammonia, SO2, they are highly soluble in water because of the hydrogen bonding interaction, as you know, and this is not only hydrogen bonding interaction but also ionization, complete ionization and hydrated ions. Now the law that we are going to study here, this is the Henry's law, is not applicable to these at all when they undergo dissociation or any chemical reaction with water. Ammonia, SO2, yes, to large extent Henry law will be applicable, but there will be some departure. But for these gases, Henry law is the perfect. Of course, under low pressure condition, not as high pressure as 20 atmosphere or 30 atmosphere like that, or 100 atmospheres, not that. Maybe 5, 10 max. Many gases dissolve with chemical reaction like chlorine, bromine. They react. Chlorine gives hypochlorous acid, HOCl and HCl. So also bromine. NO2 gives two acids, HNO2 and HNO3. It's the mixed anhydride. So in such cases also the Henry law that we are going to study will not be applicable. Now this is the nature of gases that also determines the solubility. Polar gases are more soluble in water, non-polar gases are less soluble or sparingly soluble in water. Now the next point is temperature. Solubility of gases decreases with increase in temperature, which can be explained by Le Chatelier's principle. The dissolution process is exothermic. When any gas is dissolved and the hydrated gaseous molecule is there inside, ammoniac, a very small part of ammonia is dissociated into ammonium ion and hydroxide, and as you know, ammonia is a very, very weak base. And the question of nitrogen, oxygen, that doesn't arise. There is no chance of any ionization. They are all hydrated inside. Right? And a lot of heat is evolved. So any dissolution of a gas is exothermic. So when you increase the temperature, the system will try to reduce the temperature by absorbing heat, so that the endothermic process will be favored, the backward process will be favored, more gas will be expelled out, so the solubility will decrease. You can also express in another way using kinetic theory. You increase the temperature, then the kinetic energy of the gas molecules inside will become more, and they will try to separate themselves from each other inside water, and some of them will escape out from the surface, thereby solubility will be lowered. Now, the most important factor that influences solubility is pressure. Pressure of the gas, which is in equilibrium with this liquid gas mixture. For example, you have a container containing water, any solvent say, and you have kept a gas, maybe air, nitrogen plus oxygen, plus a lot of other things, argon, carbon dioxide, whatever. And if you keep it for some time at a particular, say 1 atmosphere pressure, then equilibrium will be reached, so that whatever is the solubility of the respective gas, they will enter and dissolve. N2, O2, argon, every gas will dissolve. However small solubility one can have, but there will be some solubility. So when the equilibrium comes at a particular pressure, then we apply Henry's law. How to find out the partial pressure of any gas, because there are so many gases. So if the total pressure is 1 atmosphere and nitrogen has a mole fraction of 0.6, for example, actually it's not 0.6 in air, I am just hypothetically saying that nitrogen in some air is less, oxygen is more. So supposing the mole fraction of nitrogen is 0.6, in that case, and oxygen supposing 0.3, and other gases rest 0.1. So Raoult's law will tell you it will correlate between the liquid composition with the gas pressure. Just like in a binary liquid mixture, Raoult's law correlated the partial vapor pressure of any gas in the vapor phase with the liquid composition. And the proportionality constant for each was the vapor pressure of the pure liquid. But here, in this case, one of the components is a gas. It doesn't have any liquid state, so we are not dealing with any liquid state of that gas. So there will be little difference here than what we found in the Raoult's law, that we shall see. So solubility of gases increases with increase in the gas pressure. Obviously, when you compress the gas more, so instead of 1 atm, you hold it in your hand and compress to 2 atmosphere, for example. You apply all your strength. You apply all your strength to increase the pressure to 2 atmosphere. In that case, the gas molecules will be compressed here and more of them will enter. proportionately, depending on the mole fraction, more molecules of gas will enter into the aqueous phase and solubility will be more. So, more is the pressure, equilibrium pressure above the liquid solution, liquid mixture. More is the solubility of that gas. That is quantitatively studied by Henry's law. Let us know how. Now this is the same diagram. I have copy pasted from some source that this is 1 bar, say 1 atmosphere. 1 bar and 1 atmosphere, they are nearly same. 1 atmosphere is little more than 1 bar. 1 atmosphere is about 1.01 something bar. Right? So, this is 2 bar, where more number of C, there were 3 molecules of gas inside, just an understanding purpose. So here, when you increase the pressure from 1 bar to 2 bar, more number of gas molecules are now hydrated or buried inside the aqueous phase. That means they become dissolved. The solubility becomes more when the pressure is more. Right? So Henry law will be expressed in so many ways. So to avoid any type of confusion, this is the law where students are often confused. Which law? There are several expressions. Which law to use to solve numericals? I will tell you, don't worry at all. Now, there are 2 forms. Basically, there are 2 forms. One related to Raoult's law. You remember Raoult's law for binary liquid mixture, the left side, the y coordinate was the partial vapor pressure. And the right side is equal to mole fraction of that component in the liquid phase multiplied by a constant. And that constant in that case is the vapor pressure of pure liquid. Here, the relation is very similar. The y coordinate will be the equilibrium gas pressure. The equilibrium gas pressure above equilibrium gas partial pressure, because there might be more than one gas above a liquid. So the equilibrium partial pressure of any gas is equal to mole fraction of that gas in the liquid phase into a constant. Here, in place of the vapor pressure of pure liquid, we have a constant called Henry law constant. Now, most of the literature, or early literature, will be making use of the Henry law similar to Raoult's law. They will first write the partial pressure of the gas over the liquid is directly proportional to the mole fraction of the gas in the liquid phase. Now, see the correlation. Supposing this is a component, any component starting from mole fraction 0 and it is increasing. This is the Raoult's law. This is the partial vapor pressure of this component 1, whose mole fraction is gradually increasing. This is the ideal solution. But in reality, this is a positive deviation, non-ideal solution with positive deviation, where the vapor pressure becomes more because the intermolecular forces are less. But here, this is only a gas, no liquid, a gas. So it will also give a straight line, but having much greater slope than the respective binary liquid mixture. So here is the gas component. This is the increasing mole fraction of the gas component in the liquid. This is gas 0%. This is water 100%. So this will be gas 100%, which is impossible, unlike the case of a binary liquid mixture. You can have each liquid in the pure state, but gas cannot be, gas will be in the pure state, no doubt, but it's not mixing. It's a totally volatile gas. So we are not supposed to come to this stage because we are adding a gas with liquid. We can apply more pressure. Pressure becomes more because gas is much volatile than a liquid. Therefore, much greater pressure is required for a little mole fraction of the gas dissolving in water. So the question of increasing the mole fraction to a large extent doesn't arise. And the Henry law will fail. So this is correlated to Raoult's law. Raoult's law is for binary liquid mixture. For the other liquid, the graph will be like this. Other liquid, say water, this is ethanol, for example. If it is water, it will be like this. And this is the total one. We are not doing that. We are just correlating between here the two components are gas and water. Gas is a component which is increasing in its, this is a decreasing mole fraction of water and increasing mole fraction of gas in a particular liquid solvent, right? This is water 100%. I'm sorry, water 0% and gas 100%. This is gas 0%. And you cannot go to 100%. You can, in that case, you cannot get 100% gas, 0% water. Water, if you continue to increase the mole fraction, you have to go to the sky. You see, you have to go to the sky. Such a high pressure is not possible to increase the solubility. So such a situation will not arise. We shall be discussing only a small little portion to some pressure where the solubility, this is the solubility, the mole fraction of gas means solubility will go on increasing with increase in the equilibrium gas pressure. So the law is like this: the equilibrium partial pressure of any gas over the solution is directly proportional to the mole fraction of the gas in the solution, temperature remaining constant. Now see, Pg is the partial pressure of that gaseous component, is directly proportional to the mole fraction of that gaseous component in the liquid mixture. So is equal to, in the place of PA0, that is the vapor pressure of pure liquid, there is no liquid here. So there is a constant called Kh, that is the Henry law constant. And particularly to distinguish between the other Henry law constant, which confuses many students, I have given a term which you will not find in many books, Henry law volatility constant, where more is the Kh value, that means more is the volatility, less is the solubility. So solubility and Henry law constant are inversely related at a particular pressure. Hold on, I will explain to you. So this Kh is a constant for a particular gas, and that is fixed for a particular temperature. So Kh is fixed for a particular gas and for a particular temperature. So Kh is equal to Pg by Xg. And if pressure remains constant, then the solubility, the mole fraction of gas means its solubility is inversely proportional to the Kh, the constant. Right? So solubility is inversely proportional to the Henry law constant at constant pressure. For example, 1 atmosphere. We'll see whether oxygen is more soluble in any water body, or nitrogen or hydrogen or helium, that we'll see, because for all the pressure is 1 atmosphere. The equilibrium pressure of the mixture is 1 atmosphere. Or say you take only one gas above a particular liquid in a closed system having a particular equilibrium pressure 2 atmosphere or 4 atmosphere. You apply the same law. Now therefore the unit of Kh is pressure unit, because mole fraction has no unit, it's a simple fraction, and therefore Kh has the same unit as pressure, either in atmosphere or bar or since it is a high value, often it is expressed as kilobar or kilopascal and something like that. Atmosphere unit is the, whenever you find in any numerical the kh value, the unit is bar or atmosphere in atmosphere unit, then 100% you will be sure you will be applying this Raoult's law like Henry law, where you take the y coordinate as pressure, right? So where Pg is the equilibrium partial pressure of the gas over the solution, Xg is the mole fraction of the gas in the solution, right? Now this is the graph. X coordinate is the mole fraction of the gas, and the y coordinate is the partial pressure over the solution, the equilibrium partial pressure, and it linearly goes on increasing. The solubility goes on increasing with increase in pressure. And the slope is nothing because Pg is equal to Kh into Xg. So undoubtedly the slope is nothing but equal to the Henry law constant. So Henry law constant is determined from the slope of the graph between the equilibrium partial pressure of a gas and its mole fraction. That means solubility expressed in mole fraction. So more is the slope, more is the Henry law constant, and hence less is the solubility at a particular pressure. We just explained before that for a particular pressure, if you compare between different gases, you will find solubility and Kh, they are inversely related, right? Now see, I just read out the Kh value in kilobar. Helium and hydrogen, 144.97, 69.17. A huge difference, which is in kilobar, Kh value. So looking to the Kh value, you can compare the solubilities. Hydrogen is more soluble than nearly 2 times, more than 2 times, nearly 2 times more soluble than helium, because less is the Kh, more is the solubility at constant pressure, 1 atmospheric pressure, for example, in any water body. And see, nitrogen at 293 Kelvin, this is Kelvin, this is Kh in kilobar, and this is gas. Nitrogen at 293 and oxygen at 293. See, which is more soluble at the same temperature? Obviously oxygen is more soluble, its Kh is less, nearly 2 times less. So oxygen is comparatively more soluble than nitrogen at any temperature. If you raise the temperature 303, it increases, Kh increases and solubility decreases. Kh increases, solubility decreases. So even in 303, at 303, oxygen is more soluble than nitrogen. So you have to compare the Kh values at a particular temperature and then order the different gases in the decreasing or increasing manner of their solubilities, right? Now this is a long profile of different gases. Carbon dioxide, this is again in kilobar, the same, but in 290, that is in room temperature, 298 Kelvin or 25 degrees Celsius, right? So out of all the values, you have a glance at these values, you will find that the maximum Kh value is 150 kilobar, that is for helium. So helium is the least soluble. And formaldehyde, which is a very, very poisonous pollutant in the air, formaldehyde has a Kh value as low as 10 to the power minus 5. So you can well imagine to what extent it is soluble. It is highly soluble. So the Kh value is so low. And in between you find, these are, if you compare between, I ask you, you compare between helium, oxygen, nitrogen, carbon dioxide and argon. Only these 4 familiar gases, tell me which is most soluble. Argon, look to argon, 40. And look to carbon dioxide, it is only 1.67. So undoubtedly carbon dioxide is maximum. Then between argon and oxygen, You see, argon is 40 and oxygen is 43. So definitely argon is slightly more soluble than oxygen. Then oxygen, we already know oxygen is more soluble than nitrogen. And nitrogen is 91, much less soluble, 2 times less soluble than nitrogen. So in this way, you can have a feel about the relative solubilities of different gases, right? If it is ammonia, I have not given you the value of ammonia. You can find, we have taken a numerical to find the KH of ammonia. It is huge. I mean not huge. It is similarly, it is very small, like formaldehyde. In this particular unit, kilobar unit, it is very, very less, even lesser than formaldehyde. Ammonia is also a very polar gas. It may not be lesser than, as I just told you, I withdraw. I do not have a ready reckoner as to say convincingly that it is more soluble than formaldehyde. It is soluble, much more soluble, but between formaldehyde and ammonia, I cannot give a judgment now. Let's proceed. This is graph, partial pressure of a gas in the y coordinate. Whenever you find y coordinate is partial pressure and x coordinate is the mole fraction or solubility, then it is Raoult's law type. It is analogous to Raoult's law. It's Henry law, no doubt. There is a KH, not PA0 or PB0. It's the Henry law, but it is very, very similar to Raoult's law. In that case, you will find less is the KH. For example, carbon dioxide, the slope will be coming 1.6 kilobar. So its solubility is maximum between these three chosen. And KH for oxygen will be, the slope will be more, that is 43 kilobar, less soluble than carbon dioxide, and it is least soluble among the three, having a slope of 91 kilobar. So more is the slope, more is the KH, less is the solubility that we already have ordered before. Now coming to temperature. If you keep the gas fixed, say oxygen, we take oxygen constant and measure the slope at different temperatures. 5 degree centigrade, that is at a low temperature, cold condition, we apply pressure and see the solubility, and 15 degree, 25 degree. So the minimum slope will be at the lowest degree so that it is more soluble. We already know more is the temperature, less is the solubility. We had applied LCP. What is LCP? Least Atelier principle we had applied. We know more is the temperature, less is the solubility. Conversely, less is the temperature, more is the solubility. More the solubility, less is the Henry law constant. This Henry law constant, I again reiterate that it is Henry law volatility constant, because more is the case, more is the volatility, less is the solubility, right? Therefore, in cold climate, in cold countries, when the ocean temperature is 0 or sub-zero, aquatic life is more sustainable because the oxygen content in water is much greater. Solubility increases at a lower temperature, so aquatic life is more sustainable at a low temperature condition in cold climate, right? So solubility at 5 degrees is greater than 15, and as you continue to increase the temperature, the slope increases, KH increases, solubility decreases, right? Then this is a problem for you. Nitrogen gas is bubbled through water. I repeat, nitrogen gas is bubbled through water at 293 Kelvin till equilibrium pressure of nitrogen was achieved to be 0.987 bar. Calculate the number of moles of nitrogen dissolved in 1 liter of water. In 1 liter of water, what is the number of moles of nitrogen that can be dissolved under an equilibrium pressure above the solution equal to 0.987 bar? And the KH value is given. The moment you see the KH value that comes in the unit of atmosphere, I mean pressure, then you will be sure that I will be using the Raoult's law type of Henry law, that is pressure will be coming first in the y-axis. Right? So to save time, I have calculated for you, just to save time. Now use this Henry law, Pg is equal to Kh into Xg, where the equilibrium pressure is 0.987, is equal to Kh is given 76.48 kilo. You convert kilo to 10 to the power 3 bar, because the units have to be uniform. Here it is bar, here it cannot be kilobar, it has to be bar. So 10 to the power 3 into mole fraction of the gas. So I got the mole fraction Xg as 1.29 into 10 to the power minus 5. That is the mole fraction of the gas, nitrogen gas in water. What does it mean? It means in 1 mole solution, this many moles of nitrogen is there. So 1 minus that, 1 minus this will be the number of moles of water in 1 mole of solution. So intuitively, intelligently, we will not be foolish to incorporate this calculation. So this is approximately equal to 1. So this is so small in the face of 1 that we immediately say, so the number of moles of water is 1. So 1 mole of water means 18 gram. 18 gram means 18 milliliter, because fortunately the nature has made the density of water as 1 gram per milliliter approximately. So 18 gram will be approximately 18 milliliter of water contains these many moles of nitrogen. So 1000 milliliter or 1 liter of water or solution will contain 7.16 into 10 to the power minus 4 moles per liter. So such is the poor solubility in moles per liter or molarity. And we found out we first got in mole fraction, then we converted the mole fraction into molarity, taking the advantage that the solution is so very dilute that the number of moles of the solute, that is gas, is so insignificant that the number of moles of water is same as 1. In mole fraction, if gas is so negligible, then water is almost equal to 1. Taking that into our advantage, and that the mass of water is same as its volume, because the density will not change at all in such a dilute solution. So mass will be equal to same 18 milliliter, 18 gram is equal to 18 milliliter. Taking this approximation, we got the molarity of the gas, that is solubility expressed in molarity. Now let us take up another problem. How many minutes gone? Let me check. This is 33 minutes. Okay, this villain has come. Kh, that is Henry law constant for oxygen, is this atmosphere, not in, because its kilo is embedded here, so it should be 43.4 kilo atmosphere. There is a slight difference between atmosphere and bar. So anyway, 4.34 in 10 to the 4 atmosphere at 25 degree Celsius. If equilibrium partial pressure of oxygen in air is 0.4 atmosphere, calculate the concentration of dissolved oxygen in moles per liter, that is molarity. Exactly same type that we did, so there is no need to discuss. Same thing here, 0.4 atmosphere is the equilibrium pressure of oxygen, and this is the Kh. You got the mole fraction, and the number of moles is of water, solvent, is approximately equal to 1. So 18 ml contains this many moles of oxygen. So 1000 ml contains how much? You find this is greater than the previous one. This is, we know that the Kh, from the Kh value we already know, we have an impression that nitrogen has lower solubility. And also we got in molarity, it is 7.16 10 to the power minus 4. Here it is 5.11 into 10 to the minus 3. So we knew from our common sense, by comparing, the only difference was There the partial pressure of nitrogen was a little more, 0.98 something bar. But here it is 0.4. So that also counts. That also counts. The equilibrium pressure is more, means solubility is more. So had it been 0.4 there, the solubility would have been still less than what we got in the previous numerical. So let us enter into another, the same type. The same type, but instead of mole fraction in the right, some people, they use molarity. Same Raoult's law type, but instead of a pure fraction number, they use an unit molarity. So in that case, the unit of kH will be atmosphere, moles per liter. This is moles per liter. Liter will be crisscrossed. So atmosphere into liter, mole inverse, or bar into liter, mole inverse. In some numerical, you will find the same Raoult's law type of Henry law, but the mole fraction will not be there. It will be molar, and the kH value will be given in terms of this unit. The moment you find it is atmosphere, not atmosphere inverse, atmosphere is coming in the unit, whether it is simply atmosphere or into liter mole inverse, it will be Raoult's law type. Partial pressure will come in the left, the y coordinate. So I have given some values from the literature to compare. Same thing. Here also kH is inversely related to solubility. The concept is same. The only difference is there it was mole fraction, here it is molarity, but kH is inversely proportional to molarity. If pressure remains constant, molarity will come down. So oxygen has a lower value of kH in this unit, atmosphere liter mole inverse. Carbon dioxide is much less, so more solubility. Argon you see 714.28. It is more soluble even than oxygen, slightly more soluble than oxygen, right? Because oxygen is 769, argon is 714. So less is the kH value, more is the solubility. And here helium has the lowest, 2702.7 atmosphere liter mole inverse. It has the least solubility here in this panel, right? Now we come to an alternative expression of Henry law where the coordinate will change. The solubility will come to the y coordinate, pressure will go to the x coordinate. So to the left side, solubility will come whether mole fraction or molarity or molality or strength in grams per liter, that will come to the y-axis, and pressure, the equilibrium pressure will go to the x-axis. Now have a look. Solubility of gas, here the Henry law is expressed like this. The solubility of gases in a solvent is directly proportional to the partial pressure or the pressure of the gas at equilibrium with the solution, temperature remaining constant. So in this case, the solubility can be measured either in molarity, moles per liter, or capital M, molality, moles per kg, or grams per liter, or even mole fraction, whatever. But that will remain in the left, not right. So in that case, the kH will be completely different. You know, the concept, I mean the order of solubility with respect to kH will be the opposite, because we have changed the coordinate. Now see, solubility is, I deliberately made a prime sign, gave a prime sign to distinguish between that Henry law constant where the y coordinate was pressure and the x coordinate was solubility. But here the opposite. The y coordinate is solubility and the x coordinate is pressure. And here the solubility constant, the Henry law constant is branded as Henry law solubility constant. That was volatility constant. There was an inverse relationship between the solubility and kH. But here there is a direct relationship between solubility and kH. More is the kH dash, kH prime here, more is the solubility. Because you know if pressure remains constant, then kH dash, kH prime is directly proportional to solubility. So solubility is directly proportional to the Henry law solubility constant at constant pressure. Right? So whether you take molarity. If you take molarity as your solubility, then the unit of Kh dash will be moles per liter per atmosphere. Every time you will find atmosphere inverse as the unit, one of the components of the unit, or it is moles per liter per bar, or in place of moles per liter, mostly people write capital M. That capital M stands for moles per liter per atmosphere, or moles per liter per bar, M per bar. If solubility will expressed as a mole fraction, like the previous case where Xg was in the right side, it will be simply a number, so it will be simply atmosphere inverse. This will come down, so it's simply atmosphere inverse or bar inverse. If it is in grams per liter, then it is the Kh will be grams per liter per atmosphere. This atmosphere will go down. If it is molality, it is moles per kg per atmosphere. So depending on which concentration term or unit that you are using for solubility, accordingly Kh dash. Let me not now call Kh prime. Both are Henry law constant, but being an intelligent student, you can distinguish between the two types. If you find in the unit of Kh, you find atmosphere, bar, kilobar, not inverse, then it is Raoult's law type. Pressure will come in the y coordinate, the left, mole fraction or molarity, whatever will come in the right. But if you find atmosphere inverse in the unit of Kh, then it is Henry law solubility constant that I distinguished as giving Kh prime. So whether it is moles per liter per atmosphere, or it is simply per atmosphere, or it is grams per liter per atmosphere, or it is moles per kg per atmosphere, that depends on which concentration term that you are using, right? Let us solve some problems with that. Now in this case the graph will be different. Supposing we compare between helium, nitrogen and oxygen. Here the slope is minimum, because the slope, which is the Henry law solubility constant, that is the slope. And here the slope, that is Kh, is directly proportional to solubility at constant pressure. So since the helium has the lowest slope, it has got the lowest solubility. Then oxygen has the highest Kh prime, so it has got the highest solubility among the three. Here the solubility and the Henry law constant, as we call it, Henry law solubility constant, they are directly related, right? And temperature wise also, more is the temperature, less is the Henry law constant. Because supposing you take a particular gas, say oxygen or nitrogen, then you find the solubility in the y coordinate and pressure in the x coordinate. You will find at a higher temperature the slope will be less. Because less is the slope, less is the Kh, it will be less is the solubility. So more temperature, the solubility has to decrease. From Lee-Satelier principle, more the temperature, less is the solubility. So that should have a less Kh value, so slope has to be less. So Kh at a higher temperature is less than the Kh at lower temperature. Lower temperature, the solubility is more, so Kh is more. So this is not the same Kh that we were discussing before. It is a different Kh. To distinguish that, I was calling it as the Henry law volatility constant, and here it is Henry law solubility constant. Now let us I am giving you from the literature in terms of this Kh in terms of moles per liter per atmosphere. That means solubility expressed in molarity, moles per liter. Per liter of the solution, how many moles of gas is dissolved. So you see same thing. Carbon dioxide has a higher value than oxygen. Oxygen has a higher value than nitrogen. Helium is the minimum value, 3.7, so it has got the minimum solubility at a fixed pressure. Argon has a higher solubility than oxygen. It has got a higher value, 1.3, 1.4. So all the information that we were getting in the previous KH value, same information you will get. The only difference here, it is directly proportional, there it is inversely proportional, right? Then let us solve a problem relating to this kind of KH, the Henry law solubility constant. You can know. While looking to the KH value, I am sure a boy or a girl like you can distinguish. Calculate the concentration of carbon dioxide in moles per liter. M means in moles per liter. In a soft drink bottle, carbonated soft drinks, beverages, they are all filled with carbon dioxide under high pressure. Only under high pressure, carbon dioxide solubility becomes more to enter more into the liquid phase. Soft drink bottle with partial pressure of 4 atmosphere of carbon dioxide. You imagine now the Coca-Cola, what is the other one? The Fanta or the Coca-Cola or the Limca that you drink has a lot of dissolved carbon dioxide. And the pressure is nearly 4 atmosphere above it, the equilibrium pressure in a sealed bottle over the liquid at 25 degrees Celsius. KH, I have forgotten to make a lower subscript. It's okay. KH for carbon dioxide at the same temperature is 3.1 into 10 to the minus 2 moles per liter per atmosphere, or capital M atmosphere inverse. So undoubtedly you will be using the second form of the Henry law, that you will be using solubility first, that will be using solubility first. Solubility is equal to KH, solubility Henry law constant into what? Into the pressure. Pressure will come in the x coordinate pressure. So solubility, since it is molarity, you have to find out that is molarity. So therefore it is given in molarity. So you can get immediately in molarity. So K is 3.1 to 10 to the minus 2 into equilibrium pressure is 4. So atmosphere per atmosphere, so all are uniform. So that will give you, I have done for you, it is 0.124 moles per liter, or capital M. That means for 1 liter solution, 0.124 mole of carbon dioxide is there. Quite appreciable quantity of carbon dioxide is there. Of course, you might apprehend that carbon dioxide will be remaining in the form of carbonic acid. Okay, no problem. But the moment you release the pressure, you open the lid by an opener, immediately the pressure will be reduced, the accumulated gas will go out and the solubility will decrease. As the equilibrium pressure will decrease, carbonic acid is highly unstable. It will release carbon dioxide. Carbonic acid is nothing but CO2 plus water, though held by a covalent bond, but is highly unstable. So CO2 will be released. So jolly well you can use Henry law to carbon dioxide. So the solubility of carbon dioxide in molarity is this much. Right? Another problem for you. KH of oxygen at 20 degree centigrade is this much in terms of moles per liter per atmosphere. Then tell me which Henry law you use, Raoult's law type or the opposite type? Yes, opposite type, because it is per atmosphere. What amount of oxygen will be dissolved in 1.75 milliliter of water in contact with air when the partial pressure of oxygen is as high as 1.32 atmosphere. This is a hypothetical situation, maybe a created situation where a artificial air might have been created where the partial pressure of oxygen is 1.32 atmosphere. So just follow the lines of the numerical and answer accordingly. So I have done it for you. And since this is solubility in molarity is equal to KH into the partial pressure, so you have to find out the molarity. The KH is given and the equilibrium pressure is 1.32 atmosphere. So I get the molarity this M. 1.689 10 to minus. That means 1000 ml of the solution contains these many moles. So it is asking how many grams. So into 32 is the molecular mass of oxygen gas. So these many grams. So 1.75 milliliters will contain as low as 9.458 into 10 to the minus 5 gram. Right? So you can carry on with the problems that I have given you. You can pause and solve the problems. These are similar types. So here calculate the KH of neon dissolved in water in both kiloatmosphere and moles per atmosphere. I mean moles per liter per atmosphere units. If solubility of neon is 23.5 milliliters per liter of solution at STP. Here is the problem. The problem is there is a confusion if you are not thorough in the mole concept, in basic concepts. Then you will feel as if this 23.5 ml will be added to 1 liter. No, this is gaseous. Once you bubble this many more milliliters of neon at STP, it goes into solution. The entire neon quantity will be embedded, will be buried inside 1 liter solution. So there is no longer 23.5 ml, that is gaseous volume. This 1 liter is aqueous volume. So there is nothing in common. 23.5 milliliter is something to do with the gram molar volume. 22,400 ml at STP is equal to 1 mole. So we can find out if 22,400 ml at STP is equal to 1 mole, then 23.5 ml is how many moles? That many moles of neon has entered into 1 liter solution. So don't add 23.5. This is gaseous volume. So once you know the molarity, then you apply KH can be found out. If you write this equation, Pg is equal to KH into mole fraction, Xg. You first find out the mole fraction. If number of moles you got by gram molar volume concept and 1000 milliliter of water is 55.55 moles, then you can find out the mole fraction. The moles of neon by moles of water, that is 55.5 plus the negligible quantity of neon moles, you can neglect it. So then you can find KH in kilo atmosphere, then you convert to kilo. And for the other one, you have to use this molarity is equal to KH, as we call prime, into partial pressure. Here the partial pressure is 1 STP. Oh, I forgot here. Here you have to take 1 atmosphere because STP given means the equilibrium pressure is 1 atmosphere. So it is this 1 atmosphere you have to take. And here also 1 atmosphere, and molarity you can is known. You can know because 1 liter solution contains these many moles, so that is the molarity. You can find out KH gas. But here there is a problem. There is a problem is, if at STP it is indirectly telling that the pressure is 1 atmosphere. But if you take all other gases like nitrogen, oxygen, carbon dioxide, and other things, so that the neon, you will be having a very small fraction of the atmosphere. So this is a very defectively formulated reaction, numerical, where if you take STP, it will mean the atmospheric pressure, which contains everything. So the partial pressure of neon, that we do not know. We have put it as 1, meaning that only neon pressure is 1 atmosphere, right? Here is the presumption that you have to make, that the neon partial pressure is 1, not the entire all gases, right? I have done it here. So many problems I have given, and you can have a look. These are all simple problems. You can do it, and I have done it for you. And here there is a problem on parts per billion, ppb. Now I think this one is the problem. Where is that? ppb. Yes. kH of nitrogen in water at certain temperature is this, moles per liter per atmosphere. So is it Raoult's law type or the reverse type? Reverse type. If a closed canister contains 113 parts per billion of nitrogen in water, what would be its pressure in atmosphere above that solution? Now 113 parts per billion means 113 gram of nitrogen present in a billion grams of water, 10 to the power 9 grams of water, which is same as 10 to the 9 milliliters of water. 1 gram is equal to 1 milliliter. So therefore you can find its molarity. You convert it to its to number of moles by dividing by its molecular mass by 10 to the power 9 milliliter into 1000 milliliter. So this is the molarity. Once you know the molarity, use the opposite, the reverse, as I used to call reverse Henry law. Because the original Henry law has come from the Raoult's law concept. But often throughout the world, it is more popular now to use the reverse. Pressure in right side, that is x coordinate, and the solubility in the x coordinate. So we find the equilibrium pressure is as low as 2.4 into 10 to the minus 2 atmosphere. So with this, we conclude, and this is a problem where just by looking to its polarity, you have to say which one has got a highest kH and which has got the lowest kH, both in the original, not original, all are original, both in the Raoult's law type of kH and in the reverse Raoult's law type of kH. So if you take the Raoult's law type of kH, out of this ammonia is most polar, most soluble. It has got the minimum kilobar kH and maximum moles per liter per atmosphere kH. And the minimum solubility is that of helium, so it has the maximum kilobar type of kH and minimum moles per liter per atmosphere type of kH. That you can have a look. You have a look to the table and make a mental order. Ammonia is highly soluble than carbon dioxide, then argon is less soluble than carbon dioxide, nitrogen is even less soluble. Had it been oxygen, even oxygen would have been less soluble than argon, then nitrogen is less soluble than oxygen, then helium, and that's all. So then we talk about the limitation of Henry law. I've told you it's meant for low pressure. Under very high pressure condition, for example, you go to the deep sea as a diver, as a scuba diver, the solubility in blood, nitrogen has much greater solubility than expected of Raoult's law. Henry's law. So Henry law fails under high pressure condition. Also it fails when there will be a chemical reaction by a gas, a highly polar gas or a gas which will undergo ionization or reaction with water. Then application. I have already told you in carbonated beverages, in all soft drinks, carbon dioxide is dissolved under high pressure, approximately 4 atmosphere. So that, it gives a very benign and very interesting experience while we drink it. And it comes out of our tummy, it gives and through the nose, it gives an interesting experience. You must all have experienced that. So once you open the bottle, the solubility decreases because the equilibrium pressure decreases, gas escapes out, so the solubility decreases, and the carbon dioxide which was dissolved inside liquid, that comes out. And at that time, most of them is inside our tummy, and that comes out of our tummy with a peculiar sound and interesting and very enjoyable experience. Scuba divers, I told you, in the deep sea when they dive, nitrogen dissolves more than expected in the blood. Then when they come above, to a higher level, not to the deep sea, then the pressure decreases. When the pressure decreases, outside pressure, the solubility decreases. And when the nitrogen escapes out from the blood, it remains accumulated inside veins and produce a very painful sensation called bends, and more generally called decompression sickness. So this decompression sickness, one of them is bends, a lot of bone pain in the bone and all that, breathing pain and all that happens. That is called the decompression sickness that happens. Therefore, air is diluted with helium, 11.7% helium, so that the nitrogen content is reduced, so that there is no more solubility, and that decompression sickness, it doesn't happen. So that the other one is hypoxia, that is also called anoxia. So when you go to high altitude, say mountain top, Everest or Kilimanjaro, you go to the mountain top, you will lose your ability to think clearly. The thought process will vanish. You will be simply a mechanical person without any thinking ability, because at such a low pressure, oxygen content in the blood will be reduced. More oxygen will go out because the solubility is directly proportional to pressure. Lesser pressure, lesser oxygen content, and low oxygen content in the blood, that will develop a health condition called hypoxia, or it is anoxia, that loses the ability to think properly. And aquatic life, fish and other aquatic animals, they sustain better at low temperature, cold climate conditions, as the solubility of oxygen is more. So, before I part with you, I leave you, I caution you that whenever you solve numerical on Henry's law, use the form of Henry law, either the Raoult's law type or the opposite type. Only after looking to the unit of kH, whether it is kH, that is a volatility constant, using the first Raoult's law type, or it is the solubility constant using the opposite type, that is keeping the solubility first in the y coordinate and the pressure in the x coordinate. Bye-bye. How did you feel while you have come up to this end with a lot of patience? You make sure that you have already subscribed to my channel. I am often forgetting. In fact, a professional a YouTuber should speak this in the beginning. I forget, I'm so sorry about it. So please subscribe to my channel if you really follow me. And also don't forget to give a thumbs up. Bye-bye.